discussion, and in your folder I have just uploaded recordings on the same topic, which I will repeat with your section as well. So you can find these two recordings of section B for your understanding of the same topic. So I hope that these recordings of 2-hour lectures will help you in understanding the contents of the ultimate strength design. So at the moment 21 students are online. So with section A, last time I April 20th, or it was two hours lecture. So let's check where I stopped. So we discussed. So with your section, almost I completed discussion till the slide I have. Your section and section B are almost at par. So there is no difference in the contents which I have covered with your section and with section B. So I recommend you to please watch the recorded videos with section B, because with them I have discussed 2 hours the same topic. So for your section, since I only have 1 hour in today's week, so next week we will have 2 hours lecture. But in today's lecture I am repeat the slides which I already have discussed with section B, and I may not be able to complete all those slides which I have covered with section B, but for your help, you can watch videos recorded with section B, which are present in your. Yeah. So first let respond me that how many of you are watching the recorded videos, recorded lectures? How many of you are uh, really following the recordings or the class notes or lectures which are being uploaded? MBB, मोहम्मद बिलाल, आप वीडियोस को देख रहे हैं जो रिकॉर्ड होती हैं? लास्ट लेक्चर देखा था लास्ट लेक्चर? ओके, तो कोई ऐसा स्टूडेंट जो समझता है कि फॉलो नहीं कर पा रहा वो कंटेंट्स को? सब मुतमईन है? ये जो एम है, मोहम्मद रहमान। रहमान साहब ऑनलाइन है? कैन यू अनम्यूट योर माइक? MUGHANIM then रहमान। AS रोहान .info। आर यू
यस सर।
ऑनलाइन? जी
यस सर।
जी, वीडियोस देख रहे हो आप?
सर लास्ट वाली नहीं देखी, प्रीवियस से किए हुए हैं, डॉक्टर सफीर वगैरह की वीडियो देखी हुई थी।
ओके, तो फिर अल्टीमेट स्टैंड डिजाइन समझ आ रही है आप लोगों को? जितना पोर्शन हम कवर कर चुके हैं। आप सारे स्टूडेंट्स, अगर 24 स्टूडेंट्स ऑनलाइन हैं, मुझे बता सकते हैं कि रो बैलेंस्ड क्या बला है? रो बैलेंस्ड किस बला का नाम है? सो यू आर डिफाइनिंग रो बैलेंस्ड।
यस सर।
एग्रीड एग्रीड। इतनी तो मुझे खुशी है कि किसी का न किसी को पता है। ओके देन last time I just on that unique balance steel ratio, which, let me start the recording, which will ensure applied that to classify my example to balance around the beam we are solving has such beams will at ultimate load level. Tension controlled section means such a section in which it is either at a strain of 0.005 or even bigger. So in balance, we talked about crushing and yielding simultaneously. But in this type of cross section, which we are naming as tension controlled section, failure in concrete, steel is at 0.005 or bigger in strain. So much stable. I can draw strain diagram corresponding to this desired ultimate strain. I can use the concept of similar triangles, and I can get a very useful neutral axis depth corresponding to this behavior. that crushing versus 0.005. So when I determine that neutral axis depth from similar triangles, I get a very useful answer, that is neutral axis depth, if it is less than or maximum equal to 3/8 of the effective depth, section will have the strain in the steel bars greater than or at least equal to 0.005, corresponding to crushing in the concrete. So it means for all neutral axis depths less than or equal to 3/8, we will have the strains bigger than or equal to 0.005. So this kind of section ductility results. Case under reinforced behavior, strain obviously is greater than epsilon y at failure, but it is less than epsilon, it is less than 0.005. So if your cross section is in this domain, it will be called transition reinforced cross section. And obviously, for such cross sections, your C or your A will be greater than C of the tension controlled section, which is C against 0.005 or bigger. Obviously, there is no doubt that this C will be greater than C of tension controlled, but this C will be less than C balanced. We can, rather than, I can say that C, this I can use like 3/8D. I can also rewrite it in terms of A, that A is greater than beta 1 3/8D, but it is less than A of balanced failure. So if C is greater than 3/8D but less than CB, the same remains valid for A, that A is greater than, because A and C are interrelated with beta 1. Beta 1 is 0.85 for lower grade concretes. So such a section in which A falls in between A of cross section, which is at failure 0.005 or bigger, and of cross section in which A is equal to epsilon. A is of cross section in which epsilon s is equal to epsilon y. So if you have this range of strains, although it is under reinforced cross section, but not as ductile as it will be when A will be equal to 3 by A d into beta 1 or less than that. So that is the reason for such cross sections, capacity reduction will not be 0.9. 5 will 9 when you have this condition, and 5 will be 0.65 when neutral axis will be of balanced failure. And for transition, it will be in between 0.9 and 0.65. So it will depend on how much is the epsilon s. And epsilon s will be used to estimate phi, and it will linearly interpolate between 0.9 and 0.65. So we will provide you equation for linear interpolation on next slide. Previous publications of ACI 2011 and previous one also classify one cross section in which, corresponding to crushing in the concrete, strain in the steel is 0.004. So rather than 0.005 or bigger, 0.004 was suggested in previous publications of ACI. Now in latest 2019 publication, this requirement is now not important because already 0.005 or bigger strain can make the section selection ductile. So this additional C, which is then 3/7D or A beta 1 3/7D, is now not that important because we will be placing our cross sections at C 3/8D or less than that. So finally, then we can say that if the rho in the cross section is less than rho balanced on this scale of rho, rho B will be the highest reinforcement ratio and the other extreme will be rho minimum, the minimum required in the cross section. So the rho which will fall between rho minimum and rho balanced, rho less than rho balanced but greater than rho minimum, we call them under reinforced sections. Don't get confused with the word under. It doesn't mean they are under designed or they are weak. The under reinforced sections are actually ductile sections. Out of them, there are further two domains: tension controlled section and transition controlled section. It means if rho is less than rho balanced, within this domain, there are further two subdomains. I can put one further row over here with the subscript max. So a row in this domain will be called tension controlled, and a row in this domain will be called transition control. So what is row max? That I am going to drive on the next slide. But that row max is also less than row balanced and greater than row minimum. It is the maximum allowed reinforcement ratio in the cross section for new design. And if row will be above row max, but it is still below row balanced, it will be acceptable, but phi will then take the value less than 0.9, and it will range between 0.9 to 0.65. So it is mentioned it is always desirable that section is under reinforced, otherwise failure will be initiated by the crushing of the concrete. Steel will be underutilized because steel will be in the elastic range while concrete will crush. As concrete is not a brittle, as concrete is a brittle material, so this type of failure will be sudden, which is not desirable. So in new design, we will ensure that section is tension controlled in this domain. So it is not only under reinforced but also tension controlled, so that the steel will start yielding first, then finally crushing of concrete will take place. And on this side, it is undesirable that our row is greater than row balanced, undesirable. We call it compression controlled or over reinforced. It means that when concrete will crush, steel will be below yield limit. So capacity of steel will be underutilized. Failure will be brittle without warning. In terms of classification based on neutral axis depth, I can say that neutral axis of such cross section will be deeper than balanced, and uniform stress block depth will be deeper than A balanced. So C and A of the balanced cross section we will calculate, and our section C and A will be compared. If it comes out to be greater than balanced, it will be a indication that section is over reinforced or it is brittle in failure. As I said that if your cross section is tension controlled, rho less than or equal to rho max, strain at 0.005 or bigger in steel corresponding to failure in concrete, phi will get 0.9, 10% reduction. If rho is greater than rho balanced, section is over reinforced, phi will get 0.65. Even equal to rho balanced, phi will get 0.65. However, if the section is compression controlled, but it is confined to the helically wound spirals, continuously wound spirals, like in columns, they are compression controlled and their longitudinal steel, if it is enveloped by the spiral steel, then code, considering that improved ductility in such kind of spirals, code will allow you to use 5.75 rather 0.65. So little less reduction is allowed. But in case of beam members, since beams are rarely spiraled, so if they are over reinforced, phi will get 0.65. Even at balance failure, phi will get 0.65. And for transition sections, which are between epsilon y and epsilon s is less than 0.005, but it is greater than epsilon y. Just give me 1 minute. Performing linear interpolation sections that with 2.9, it will be linearly interpolated in case ties are present as confinement, stirrups or rings, and if spiral, then from 0.75 to 0.9. So this equation will help you to get phi for members with ties and phi for members with spirals. For example, for all compression controlled sections in which strain is less than or equal to epsilon y, phi will be 0.65. For all cross sections in which strain is 0.005 or bigger, phi will be 0.9. But if strain is between epsilon y and 0.005, which are transition reinforced, phi will be linearly interpolated. So it will vary from 0.65 to 0.9. So the difference in ordinate is 0.25. In abscissa is 0.005 minus epsilon y. So the slope of this line will be 0.25 divided by 0.005 minus epsilon y. And suppose I have the epsilon s equal to this. So in order to get this increment, I will subtract from epsilon s, which is notated here as epsilon t. I will subtract from epsilon t minus epsilon y to get this abscissa. So epsilon t minus epsilon y into the slope will give me this additional phi. So then 0.65 plus this calculated value will give me the final interpolated phi. So for example, if in your beam steel is at, just for example, is at 0.003 and concrete crushed, and concrete also crushing ultimate strain is 0.003. So just a cross section in which crushing in concrete and steel strain at that instant is at 0.003. So what will then be the phi? Phi will be then, and suppose the grade of steel is 300 and grade 300 steel has the yield strain 0.0015. So it means 0.0015 epsilon t is it is the slope into 0.003 minus 0.0015. Can you give me answer from this
Sir,
equation?
0.757.
So let it be 0.76. I am truncating it to the second decimal place. So if it is spiraled, then obviously this 0.25 will drop to 0.15. So the slope will then be 0.15 over abscissa. And in this way, we can calculate the phi. Now, as I have shown you on that scale, rho max, that ideal reinforcement ratio corresponding to 0.005 strain. So the strain diagram is like this, 0.003 and corresponding to that 0.005 or bigger, and C of that. So, and if this is the strain diagram in a cross section, that cross section rho will be called rho max. So strain is equal to or greater than epsilon 0.005. So in order to get that unique reinforcement ratio rho max, again I will call the equilibrium equation. In equilibrium equation ASFS, so obviously it is the section which has yielded. So I will replace Fs with Fy, and right hand side C value I am using Whitney's uniform stress block depth. So 0.85 Fc prime A into B and AS I replaced with rho BD because from this definition that reinforcement ratio is the ratio between area steel over effective area. So I replaced AS with rho BD. I brought rho on one side. So this is almost the same equation which we earlier derived when we were discussing the balanced ratio. So the same picture, the same equation, but here the subscript was B because we were using the strain diagram of balanced failure. Now, since I am using a strain diagram of this desirable failure, when derived it on the previous slide, that will be beta 1 3 over 8d. So this we have derived that against this strain diagram, neutral axis or uniform stress block depth will be 3 by 8d and beta 1 3 by 8d respectively. So I am now putting this A over here, so then I am allowed to put max then as subscript just to signify that this is such a unique reinforcement ratio which will provide 0.005 or bigger strain corresponding to failure in concrete. Now in that case, when I will substitute A over here, this D and this D will cancel, so we will be left with this equation. 3 by 8 beta 1 into 0.85 Fc prime or Fy. So I recommend you to memorize these equations. Equation of rho B and as well as equation of rho max, because these are very useful expressions. You are going to use them repeatedly. Now for your example problem, can you calculate rho max? Okay. So please calculate rho max and then tell me the example problem. Can you calculate? Our example problem has Fc prime 20, Fy 300, 0.85, and beta 1 is also 300. Beta 1 is also 0.85, so I can make 0.5 square into 3 by 8. So can you calculate? So rho balanced, we did that calculation and we got about 3%. Rho minimum I have to calculate. Rho max, now I got this equation and I'm asking to give me rho max. Rho of our problem was 1.36%. So what rho I will get from this with calculator and with mental presence in the class? हाँ जी, कोई सो रहे हैं, सब सो रहे हैं, कोई जाग भी रहे? सी आर, प्लीज कैलकुलेट. आर यू लिसनिंग?
Sir, 0.018.
जी, 0.018. Good. So it is actually 1.8%. So let me write here. It is 1.8%. So it is important to note that our cross section under discussion has the rho less than rho max. So that was the reason in your example problem you got epsilon s almost 0.007 or bigger, because conceptually, since rho is less than rho max, so obviously epsilon s will be greater than 0.005. C will be further less than C max. This is 3 over 8 D. A will be less than beta 1 3 over 8 D. So in this way, we can use these rows for classification purpose. In quiz, vivas, interviews, these rows will help us a lot in giving quick response. So row balanced, row max, and now comes row minimum, which is another very much important threshold in our cross sections. And this transition, as I said earlier, now in latest code, this epsilon s and corresponding to this a and the calculation of row max against this transition section is no more important. So you may even ignore this in as per the latest guideline. Now the last important threshold is this row minimum. So row minimum as given in chapter 9 of ACI 2019 is another important reinforcement ratio which will safeguard cross sections against sudden failures due to fracture of the steel bars. So once the modes of rupture will come, and you have studied in your allowable stress design uncracked cross sections, the instant it will get cracked, modes of rupture will come, stress will be transferred entirely to the steel bars, tensile stresses. If at that stage steel bars are fractured or broken, it means failure will take place suddenly. So this minimum reinforcement ratio will safeguard the cross section against wide cracks, sudden failures. So we can't allow a section with the area of steel and corresponding to that reinforcement ratio less than rho minimum. So this minimum steel is always provided because concrete is cracked, then load comes on steel, so there should be a minimum amount to resist that load to avoid sudden failure. Keep in mind that this formula is not used for slabs. For slabs, when we will talk about the design of slabs, I will provide you a different rho minimum equation from ACI code. In this beam cross section, there are further two equations, and out of them, maximum will govern. First equation, use in numerator square root of Fc prime. In second equation, Fc prime is not explicitly utilized. So for our example problem, if I use this first equation, it will be 20 under root because we selected 20 grade concrete versus 300 grade steel. So based on experiments, these empirical equations are proposed in ACI. The right hand side equation gives us, and multiply the answer with 100 to get in terms of percent. So can you respond? Which out of two will govern? Because it is greater than or equal to, so out of two greater will govern. जी प्लीज अपने माइक ओपन करें और कैलकुलेटर से कैलकुलेट करें.
Sir, 1.4 over 300 times 100 is equals to 0.467.
Good. The left one?
Sir, right one.
Okay, right one.
1.4 over Fy.
जी ये कितनी है जी?
0.467.
Let it be 0.47. I am rounding up to second decimal place. And right hand side, left hand side, 0.3. 0.37. Okay. So out of two, this will govern 0.47. So we are happy that our cross section under investigation for capacity analysis is well within rho minimum and rho max. So as expected, section is ductile, and we also confirmed it from epsilon s estimation, calculation of C and A. But even without going into detailed assessment, if right in beginning you are given with the cross section and you just estimate its rho, and from the known material strengths you calculate rho minimum, rho max, rho balanced, and then compare your rho, you can very quickly decide the domain of the cross section and you can comment about the cross section type. Most desirable, less desirable because less ductile as compared to the section in this tension control domain. Phi will be interpolated, and unacceptable, undesirable, that rho greater than rho balanced. So this final slide in this presentation is just for your information that in the current publication of ACI, considering that now they are allowing the higher steel grades in flexural members even above 420. So keeping in mind that if higher grade bar will be used in flexural members, its epsilon y will get bigger. So there are chances that 0.005 may not be the safe threshold to get excessive warning and ductility. So what now they are suggesting that calculate for the steel the yield strain and then add in that a fixed value of 0.003 and use that as a strain in your strain diagram to qualify for the tension control section. So in this case, even if I still use 420 grade steel, 420 grade steel has the yield strain around 0.001 or 0.002. then plus 0.003, it still give me 0.005, no change. But for grade 300, which we are doing in our example, we have yield strain 0.0015 plus 0.003 will give me actually 0.0045. So rather than 0.005, even at 0.045, I am allowed to use 5.9. And if I am using 520 grade steel, suppose 520 grade steel, its modulus of elasticity and its yield strain will then be 0.0026. You can calculate exactly. Now this plus 0.003, the threshold, not 0.005, it will get 0.0056. So in this way, for higher grade steels, you will be keeping in mind that not just fixed 0.005, you need to look into the yield strain and then decide what threshold will be used to get 5.9. This is little modification in the latest publication, and even for transition, they are using the same between yield and this range. For compression, yes, less than or equal to yields. This is just for your information that as per the current 2019 little modification they have suggested, keeping in mind that now higher grade steel bars may be practiced in Pakistan, although 420 grade we are commonly using in our flexural members, but if in some project higher grade steel will be used for flexural members, then we need to increase the threshold even above 0.005 to avail 5.9. This is just for your information. So it is concluded. So let me stop recording. So you are only 29 present today in today's lecture. Quite unacceptable presence. So, but I recommend you to watch not only video recorded of today's lecture, but also the videos which I have shared with you recorded with section B. These videos will help you a lot in understanding the design of the reinforced cross section. So I'm trying to discuss side by side application of these equations, but finally our objective is to design a beam, not just capacity analysis but also design. So let me end today's lecture here. If you have any question, I am online, but if